All right. Hey everyone. This is Sanjay Medichurla. This is the first video in a four-part video series on vectorization, the Jacobian, the Frenet-Serre differential equations, and 3D plotting in Python. This is my homework one submission for Carlos Koh's Computational Methods course at the University of Cincinnati. So with that out of the way, what we'll actually be doing here is um, we're going to be working with this helical curve, right? This helical pipe that's parameterized by these three equations. And so in this video, we're using closure. We're going to explain and code a higher order function that accepts a function and returns the Jacobian of the helical curve. And then we're going to compare the results of the automatic differentiation with the JAX library in Python. So you can take the Jacobian, they have built-in functions to the Jacobian, but we want to uh, manually code a function for the Jacobian, right? So um, let's go over to Python. And before we actually do this whole Jacobian, let's just graph our curve, right? So if we look at this curve, I mean, it has a format that we're sort of familiar with. So x equals 3 cosine theta, y equals 3 sine theta. It looks like kind of like polar coordinates, cylindrical coordinates if z equals to z, but z is also parameterized in this case. So it kind of makes sense. First, we're going to import our libraries, import numpy as np, and then what are we going to do? We're going to say r equals 3, mz, which will be the slope of z, because z is linear, is 0.4, and then let's go. X equals r times np dot cosine t, y equals r times np dot sine t, z equals mz times t, right? And if this were a graphing calculator, we could just go ahead and graph it. But that's because graphing calculators have a set interval as to which the t-values are. Excuse me, but we don't. So what we're going to do is we have to define some values for a t, and we're going to use np.linspace to do that. So linspace, what you can do is you start with a value, you end with a value, and then you print out how many how many values you want in the set, and then it gives you an evenly spaced array of that. So if I printed out t, print t, what do I get? 0 to 100 evenly spaced. We have 101 because it's 0 to 100 inclusive, right? And then so let's think about what we want our domain to be for this. And so we know cosine and sine have one period or one revolution for cosine and sine is 2 pi radians, right? So it makes sense for us to have our interval go from extend from 0 to 2 pi, np dot pi, right? And this is cool. So what does this mean? So I'm gonna make this interval 5 real quick. And so it's a 0 pi over 2 pi, 3 pi over 2, and then 2 pi. And so what does this mean for x, y, and z? This just means x will be an array where you apply this operation to each value in our t array. And so if we did that, so cosine 0, remember cosine 0 is 1, cosine pi over 2 and 3 pi over 2 are 0, and then cosine pi is negative 1, right? So we expect our x to be 0, oh sorry, we expect our x to be 3, um, 3, 0, negative 3, 0, and then 3. So if we print x, we should get that. Yeah, so 3, basically 0, negative 3, basically 0, and then 3. So here we go. I'm going to change this back to 100. And then let's go ahead with graphing it. So to graph it, we have to import another library. So from plotly dot subplots import make subplots. This is how we're going to make our function. Yeah. And then so we're going to say the figure is make underscore subplots. And then what do we want to do? We want to make a scatter plot. So figure dot add um, add scatter 3D is what we want. Thank you, Python. I was definitely forgetting my syntax there. X equals x, y equals y, z equals z, And then let's just see what it looks like. Nice. Actually, I'm gonna do one thing real quick. Mode. I just want it to be a line, so a bunch of dots. Lines. Nice. And so this is our curve, and this is one rotation or revolution of our curve. So you can see it goes all the way back to x equals 3. Um, and so, uh, oh, don't zoom in, stop. So if I wanted to do multiple rotations, so let's say I'm going to get crazy with it. Let's say if I want to do 10 rotations, right? I can make this 20. Look at that. It's rotated around 10 times, and then you get the -3. Um, and so for us, I think we want to see a couple rotations. Just maybe 2 rotations is fine. So let's just make this 4. All right. So we've graphed our curve, we've graphed our helical pipe, and now we want to find, what do we want to find? We want to use closure. So what is closure? And I'll pull up the definition for you real quick, and then I'll explain it. So use let's say closure in Python. Hey, you can tell I googled this. Um, Python. Let's see, what is closure in Python? It's a function object that remembers values in closing scopes even if they are not present in the memory. So basically, it'll remember values even if they are declared outside the function. And then this is useful because you don't have to rely on global variables. And for some reason, if you delete your function, you can still calculate, you can still call the closure function and get our result. So basically, to do that, we're going to need an outer and an inner function. But more on that in a second. Let's actually figure out what is this whole Jacobian nonsense. So the Jacobian of a vector valued function is a matrix of all of its first order partial derivatives, right? So that's very important to us. And so we look at the way it's defined. You have a function. Um, you have a function. Um, and then you take its derivative. All of the rows are a derivative with respect to independent variables. So like it could be df dx, df dy, df dz, so on and so forth. And then here, going down, it would be if you have multiple functions. So let's look at our example, right? We have multiple functions, x, y, and z, correct? Now, what do they depend on? They are all functions of t, right? If we were going to write this, we would say x of t, y of t, and then z of t. Now, if they were changing, right? If they were changing, for example, if it was like, if it depended on r and m, for example, then it would become x of r comma t, right? They would depend on both of them. But here there's only one independent variable and then 3 functions. So the dimensions of our Jacobian should be 3 functions, and they're all taking the derivative with respect to the one independent variable, right? And so when our Jacobian is like this, when there's only one independent variable, it is equal to what's called the gradient. And so the gradient uh, is basically the matrix of all its derivatives, um, is the matrix of all derivatives. Uh, and so you see this little del operator, right? That's used for a lot of things. You can use it for divergence, curl, things like that. But it's important that you apply the gradient to a function, like it's del function, not del vector, because then you're going to get a bunch of like a second order tensor, I think. But the result of a gradient is a vector of that function's derivatives. That's the whole point. Um, and so here now we know our Jacobian is going to be 3 to 1. Sorry. Yeah, 3 by 1. And so let's let's start coding this. So I'm going to comment this out so we get a little bit more room on our screen. Yeah. Um, okay. Next. And so first I'm going to define a function, so f of t, and then this function is going to equal basically the function we just made. Because if you look at the problem statement, we want it to accept a function as the input, so we need to define a function. And so what should this return? Well, ideally we'd want to return this function with all its parameters in one thing. So we're going to say xyz equals numpy.array of x, comma y, comma z. And then so now our function is in one array. Okay, so here we go. We have defined our function. Oh, let's take out the t p dot one space. And so normally when we calculate Jacobian, we calculate the function at multiple values, excuse me. But here, since we're doing this kind of analytically, we are calculating the Jacobian at a single point. Or and if this depended on r as well, we would say f of t and then r. Or we could have you could have t come in. Yeah, you'd want f of t and then r, and do it this way. Mm, so back to what we are doing. So let's make our outer function get the Jacobian. Jacobian. And then the inner one's just going to be Jacobian. You can see it has some memory of when I was practicing doing this. Um, and so what is the Jacobian? What is the argument here? It should be the function, right? F. And then what is the argument here? Well, we have to think about how are we going to analytically compute the definition, like the derivative. So let's Google the definition of the derivative, of a derivative. So before we learn all this power rule, chain rule, product rule stuff, we learned the definition of a derivative. So limit at h approaches of 0 of f of x plus h minus f of x divided by h equals f prime of x, right? And so we're going to use this and calculate the derivative for each of our functions in for our helical curve, right? So this is going to take in x naught and then h equals a very small number because if you look back, h approaches 0. And then so what is this x naught? It's like the point about which we are going to be computing our derivative. And so x naught could be an array because if this was f of tr, x naught would give you a point for t and r. So it's not necessarily just an integer. It could be could be an array of size 1, and so on and so forth, right? And so uh, before we start populating our Jacobian, we want to know the size of it. And I've given you a hint just now. I said x naught would contain specifications for all of the variables. So like x equals 5, r equals 3, t equals 5 could be one, or just t equals 5 in our case because t is just the only dependent variable. And so if we went back to our Wikipedia page, we said that dependent variables tell you the number of columns, or sorry, independent variables tell you the number of columns. So we can say columns equals x naught dot size, right? And then so how do you find the number of rows? The rows is the function, right? So if I apply, or let's say, um, let's say f naught equals f of x naught. Maybe this is better to call this a's, but it doesn't matter. Rows equals f of x naught dot size, right? And then the Jacobian j will have, we're going to make the zeros for now, but it will have size of rows column. Uh, nice. So we have the size of our Jacobian down, and then now we have to find the, put in the actual values. So this is where we're going to do the f of x plus h stuff, right? So first we're going to say for I in range column. So we're going to iterate through um, uh, the number of columns in the Jacobian, and that should equal, so we're going to iterate that many times. So how many of our columns are there? That's how many times we're going to iterate through this. Um, and so what we're going to want to do is uh, for I in the range columns, right, we're going to say x, we're going to make a copy of x naught real quick, and I'll explain why in a second. np.copy x naught, because we're changing x naught, right? We want x naught not to change, but we're doing this whole f of x plus h thing. It needs to be stored in a new array, so that's why we're doing that. Um, and then so x at I equals x naught at I plus h. And so this is just the x plus h part of our function. And then so to do the f of x plus h, what you're going to do is the Jacobian equals, so we're going to say f of x minus, what is it, f of x naught, and then all divided by h, that equals your derivative, right? And so we want to add that to our Jacobian matrix. So we're going to say the Jacobian equals this. Now, where in the Jacobian do you want to add this? Um, we want to add it. Uh, we want to add it in column. Sorry, um, in column I. So we're gonna do it like this. Um, and we're gonna say in column I. And then we're gonna come out of the loop. We're gonna say return J, and then we're gonna not return Jacobian. Return J, and then the outer function, because we're using closure, we want to return just the function Jacobian. And then when we set something equal to this outer function, it will take on the type of function, and then we can go from there. So, I mean, let's just run this, make sure like I didn't do anything wrong. I guess we'll know in a second, right? So I'll say my Jacobian equals get Jacobian of f, because f is a real function now. Um, and then let's return, or let's say my jack. So now my jack takes the properties of Jacobian basically. So let's put in a point. 0, that's a float. Now, if you're watching this, I want you to take a second and think to say if this is going to work. So pause the video, see if it'll work, if it won't work. I'm going to tell you now, it doesn't work. Um, oh, sorry. One thing is you shouldn't have the parentheses if you're going to use closure here. It should just be uh, return Jacobian. And so float object has no attribute size. So we put in a 0, but we ask for its size. Now that means this should be of type array or type list. Now that's not so good for us. We kind of just wanted to input our function and put in a point, right? So what we should do here is use what's called at least 1D. It's a at least underscore 1D. It's a numpy thing. And so what it'll do is it'll take an input and if it doesn't have a dimension, it will make it an array of size 1. So that way we can get around this whole array type nonsense. Um, and then one thing I will, and then, so let's see what happens if we run it now. Float object has no attribute size, but we fix this. Now it should be fine. Oh, no, no, this isn't right. So we should say x naught. We have to make it one dimensional. And then we have to say the columns equals x naught dot size. And then this should work. Numpy dot 60 float 64 object. Um, uh, f0. I don't. This should just be f of 0 dot size. Sorry about that. Well, this is why we run the code, right? We want to see if there's anything wrong with it. And then there should be one other thing wrong with it. It cannot interpret 1 as a data type. Um, so why is that? It's because the dimension of your array should be in a tuple like this. So that should take care of that error. And then if there's one other error, could not broadcast the input for array of shape 3, 1 into shape 3, comma blank, right? So basically, these array sizes are not the same. So what I'm going to do is I'm going to broadcast the right hand side to be the same dimensions like this. And look at that. We've run an array of 0, 3, and 4. So let's see if this is right. So our function is 3 cosine 3, 3 sine of t. So if I were going to do this, x prime of t equals x prime of t will equal, in our case, negative 3 sine t. Excuse me, I'm sorry. Um, and then y prime of t will equal y prime, typing is hard, yeah? Equals 3 cosine t, and then z prime of t equals 0.4. I can write these as the primes and stuff, because I just don't have the partials in like the good notation, but yeah. And so if I put in 0 here, sine of 0 is 0. Cosine. Cosine of 0 is 1, so it should be 0, 3.4. So we know our Jacobian works, but let's compare it. Let's compare it with the Jack's Jacobian, right? So I'm going to Google Jack's Jacobian. So let's see. There's like a GitHub, or here, let's see. Jack's documentation. Um, so we want to import jax.numpy as JNP. That's probably the first thing we want to do. So Jax is its own library. It's not the same as numpy, so we have to change a few things. Import jax. What is it? Import jax.numpy as JNP. Numpy as JNP. Right? And so I'm going to want to redefine this as a Jax array instead of a regular array. So I'm going to say fjax, and then I'm going to say, oh, goodness, a JNP array, right? And then let's go back to our documentation, and then let me just find the Jacobian. Um, So what can I do here? Um, both Jacobian matrices, the jack forward and jack revision functions, right? Um, but there's another thing we can do. So let me pause this until I find the actual Jacobian that we could use. All right, so I figured it out. I was just being really dumb real quick. Um, so we were trying to find the Jacobian, right? And so I forgot that we have to import jacks. Kind of important, right? And then if we go down here, right, we can just say the jack's Jacobian equals uh, equals what's going to equal jacks dot Jacobian of our new f jacks. Except we're going to cast a function, so we're going to say lambda t, which is we're just writing the function inside the function, right? So if you're not familiar with this lambda notation, it's just like the lambda a equals a plus 10, for example, is a function, and then when you give it a, it'll give like a value of 15. Like if you give a as 5, it'd be 15. So here we'll say lambda t, goodness, lambda t equals f jacks of t, um, and then we're gonna say compute the jacks of Jacobian 0, because that's what we were doing earlier. Okay, so we got some error. What is it? ND numpy. Oh, we have to make this JNP. Yes, yes, yes. Here we go. Okay, and look, we get 0, 3, and 0.4. Except we get it horizontally. Um, I'm not so sure as to why. I think based on this Wikipedia article, it should be vertically. Though in other applications, I've seen where sometimes they'll define the Jacobian as a transpose of this. And I'm a, I personally am not so sure as to why that happens. But if we put in my Jacobian 0 point, we can see we're gonna get we're gonna get 0, 3.4. So they are in fact equal. And so if we look at the problem statement, we definitely use closure, and then we coded a function that calculates the Jacobian of the helical curve, then compare your results in one with that obtained via automatic differentiation with jacks. So I think we did all of that, and so I will see you in the next video for part 2. Thank you.